So, welcome back, and as ever, I do hope you and your family are keeping well at this time. So, what we're going to look at in this video is the national grid. It's something that I think you probably know a little bit more about than you thought you did. So, the first thing we've got to look at is what is the national grid? And that's a question that comes up at GCSE from time to time. And I'm going to use a little bit of language here that might not make sense, but I'll explain it in a minute. So the national grid is something very specific. If you look outside, you've probably seen those really dangerous high voltage cables on pylons, those great big towers that carry the electricity between towns and cities. And if you look at those pylons and cables, you're looking at a little bit of the national grid. But there's another bit that you need to include, and then you fully understand what the national grid is. So here's a new word. What the national grid is the transformers and the cables between the power station and basically the city or the town where the power comes in. So I'll write and towns and cities. Okay, so you'll notice that the national grid consists of two components. Okay, transformers, which we'll explain in a minute, and the cables that are between these transformers. You'll notice it is not the power station. Okay, it's the equipment between power stations and towns and cities. It's the transmission system. Okay, and one of the guys who invented a lot of this material and the ideas for the national grid originally was a chap that I think when I was at school most people would never have heard of, and it was Nikola Tesla, a Serbian American. But of course, with the car and things at the moment, which isn't really connected to him at all, the name Tesla has become famous. And Tesla was a bit of a genius, and Tesla realised that to get electricity from a power station to towns, especially ones that were a long way away in America, we needed a grid system of cables, and didn't work very well. So we needed something to boost the electricity on those cables. We needed transformers. So that's what we're going to look at now. So let's now look at the design of the national grid and what it is. Okay, and if you were in my class and one of my students, I'd probably go off on a long one now about Nikola Tesla and what a genius he was, etc. Because he really was. He was light years ahead of his time, and he thought about this. Okay, we'll do a little bit of history at the end of the video, but just to say that in the early days, power stations were built right next to cities and houses, and the transmission cables were very short. Okay, now think about the environmental nature of that, coal-fired power stations being close to houses, and the fact that that company couldn't sell its electricity right the way across America because the cables would be so long that there'd be so much loss of power on those cables that the energy would never get there properly. It would all be wasted in warming up the cables, kind of like a mini stretched out toaster. And Tesla had the answer to this. So you're going to put up with my drawing skills here. I'm going to draw over here the power station. So there we go. Cooling tower, and next to it the power station main building with its furnace and generators, etc., and chimney. Remember the steam coming out of the cooling tower, not pollution as such, whereas out of the chimney, that's a different matter. So here's our power station. Okay, and over at this side of the page, I'm going to draw our sort of city, and I'll draw a sort of factory kind of icon here. Okay, and there's a factory and town, etc. So in case you aren't clear on what that is, let's write that in. Okay, now there's some distance between our power station and town, and we want to get electricity from here to here. and we don't want to lose energy on the way. Now, you remember that cables have resistance, so when you pass electricity through them, you pass current in amps, they will lose energy as heat. So the longer you make the cable, the more resistance it's got, and if you draw power from the far end, okay, the current going through the cables, the amps is going to warm them up and lose energy, and that's a bad thing. So I'm going to keep it simple, but what we do at the power station end is we go into something called a transformer. And the transformer does something really clever. Okay, it takes low voltage electricity and it boosts the voltage up massively. No moving parts at all. It's a really clever electromagnetic device. And it does it, simple bit on this now, this is not a lesson on transformers. It does it by having lots of coils of wire, okay, close to, on a big iron block, some other coils of wire, but here's the clever bit. Many, many more of them. So you'll see there's some coils of wire here and many more there, and it's built on a big block of iron. Okay, you've actually seen these, and in a minute I'll put up a picture of a transformer that appears right at the other end of this. Okay, so we're going to generate electricity. It's quite a high voltage at a power station, about 25,000 volts generation. Okay, 25 kilovolts, but even that is not a high enough pressure or voltage to pass the electricity over the power lines. So we're going to go into our transformer that sits outside the power station. I think some of you may know what we're talking about here. You sometimes see the other end of this in towns and cities, all those wires and insulators and that buzzing sound, because you've got AC electricity. This is an alternating current system where the electricity goes backwards and forwards and backwards and forwards, because the generators have magnets in them that go down and then up and then down and then up, that create electricity that changes in voltage. Alternating current doesn't work with DC, and that's a whole other story about Tesla that I won't go into. Okay, so there we go. Here is our transformer. And this transformer is going to take the voltage and multiply it up. Okay, you've got a few turns of wire here and lots there, and the ratio between those, this might be 1 lot to 10 lots, will be the multiplier for how much we step up the voltage. Okay, and normally on the power grid, on the national grid, we step up to a very, very high voltage indeed, about 440,000 volts. Okay, so we need to get those cables away from people. We need to get them well off the ground because they're difficult to insulate, and there are other reasons why we have them high up. And so to do that, we need to build pylons. So I'll draw a pylon here. So you've seen these electrical towers, big tall things. I think the first one was built back in the day in Edinburgh in the UK. And they have this sort of lattice construction, and then they have a crossbar on them with insulators hanging down, and we're going to hang the cable off those. There's barbed wire around the feet. You never climb them, never get on them. They're extremely dangerous places. If you've seen engineers working on these, they've turned off the line that they're working on. Otherwise, it would be so dangerous. So let's take our cables and put them up onto the pylon. So here's one, and here's the other one. Okay, and they're going to be hanging off massive insulators, remember, because there's a very high voltage on them. Let's make it an easy number, 400 kilovolts, so 400,000 volts. So be sure that that number is a lot bigger than that one. Okay, and then we're going to take that off to our town, but we've got a problem. In our town, there's no way we could use a voltage that high, so it's going to have to come into a substation, okay, and that substation is going to be jam-packed full of transformers that reduce the voltage. Here, we stepped up the voltage, and at this end we're going to step it down. Okay, and we probably won't step it down enough for houses. We're going to then step it down a second time so it's a suitable voltage for houses. So how would we step down the voltage? Well, we need a transformer. Flip this one round. Okay, so if we come into lots and lots of turns, okay, built on an iron block, and we come out with only a few coils of wire, more correctly turns, then the voltage has been stepped down, and that can then go off to the town and the city. So I'll write on these transformers that here we've stepped the voltage down, so it's a step down transformer, and here we've stepped up the voltage, so this is a step up transformer. Okay, so took me a while to get there, but now you see the national grid. But be careful, which bit of this diagram is the national grid? It's the green bit. Okay, so it's all the transformers and power lines that are needed to get electricity from a power station and to the town, but it doesn't include the power station. So I hope some of you have been thinking, but hang on, this is really dangerous. Superbly high voltages, expensive transformers, difficult to put the cables under the ground, very difficult to maintain, can be damaged by lightning and weather, etc. And if you were to touch these, you're going to fry. So why bother? Okay, and again, I'm kind of holding back on talking about Tesla and how he was insistent that systems are built using this method, and Edison and others who at the time said, oh, it's dangerous and it kills people and you shouldn't use this. But Tesla knew that it was the best way to transmit electricity. Okay, he realized that using step-up transformers that boost the voltage are going to improve things massively. They're going to enable us to get the electricity to the towns and cities over very long distances with massively reduced losses on the cables. Okay, now here's where it gets a little bit tricky, but it's still GCSE. I hope you remember the equation for power. There are lots of them, but power, and in this case the power that will be on the cables being radiated by the cables, actually warming up the cables, okay, the power loss on the cables is P, which is equal to I squared R. Okay, now this is a really, really important formula. What it says is that if we have amps current in the cable, okay, we will lose energy. But, and this is the bit students struggle with, okay, squared will be the loss. So if we have, say, 2 amps, this is not very good maths teaching, but if we have 2 amps, maybe we lose 2 lots of power, okay, for 1 ohm. But we don't. 2 squared, we have 4 times the loss. Now think what happens if we boost the current, took more electricity at this end, to 3 amps. The loss is going to be not 3 times bigger, but 3 squared, okay, 9 times more. And if we go for 4 amps, just a little bit more current, 4 squared, 16 times the loss. So amps is bad news, okay? Amps is not what we want on these cables. So how are we going to get power to people? Well, you might remember that power is also IV. And here's the clever bit, okay? Let's get the amps down. Let's not send many amps. Let's not have much current in the cable. So let's reduce the amps and boost the voltage. And now you can see the reason for the transformers. Okay, so Tesla and others realized that to reduce the amps, which will reduce the heating loss in the cables, which will mean more energy gets to the city and what have you further away, let's reduce the amps but boost the voltage. So there we go, 25,000 to 400,000, okay, So we've got a massive boost in voltage, but therefore a massive reduction in current, so much less I squared R loss. But of course the catch is, at the far end, we can't use this voltage. It's way too high, so we've got to reduce it. So for the short distances, we'll have a step-down transformer, and it'll reduce the voltage and boost the current. It's worth saying at this stage that if you have a lesson on transformers, so many people think the transformer makes energy. No, it doesn't. Okay, it's got no working or moving parts in it. What it does is it keeps the energy per second the same, okay, but it boosts the voltage and reduces the current if it's stepping up, okay, and if it's stepping down, it reduces the voltage and boosts the current by the same factor upwards. Okay, so 10 times less voltage, 10 times more current, keeping the power the same. So it's not a magical device that creates energy. So what I'd like to do now is just put a few numbers into this to show you how important it is in the national grid that we use transformers. So let's put some numbers into this quickly to show you how it works. So let's step up the voltage by 16 times. Okay, so the difference in ratios of the turns here will be 16. So if there are some on this side, what we call the primary, there will be 6 times as many on the secondary. So let's step up the voltage. When we talk about step up, by the way, we're always referring to voltage. Step up and step down, always the voltage, not the current. Let's step up the voltage by 16 times. Okay. Well, if you think about that, that means for the same power, the current, will be down by 16 times. And here's the clever bit. If you didn't understand this equation, okay, then you won't understand why the national grid does what it does, okay? But if the current drops by 16 times, we don't save 16 times more energy. The power loss is proportional to I squared. So the loss on the system, the power loss, is proportional to I squared. So if we reduce the current by 16 times, we'll reduce the loss by 16 squared. Okay, and that's a massive saving. 256 times less. Okay, so it's really important that we use transformers on the national grid to make sure that we don't waste energy as heat on the cables. So I hope you now have a good understanding of what the national grid is, and I've taken it a little bit further and shown you mathematically how we can calculate how it massively improves things. So what I'd like to do next, just very quickly, is a little bit of a history of the national grid and why having a national grid is such a clever thing. So before we finish, let's have a quick look at the history of the national grid and why it's a really clever thing in use. Okay, so it sort of started in the UK. It was Edinburgh, I think, in about 1928. So that's quite sort of early days. You've got to remember, people were, did not necessarily have lots of electrical devices in their houses. It was really only lighting. Okay, and it was properly working again approximately in 1933, and I'm told that it was built ahead of time, or at least the first part of the grid was built ahead of time, and it was built well within budget. Okay, it kind of went totally national So that's sort of all over the UK in about 1938. So that's quite important because we had the Second World War intervening at times when we actually had a grid system in the UK. So very quickly, let's look at what happened before the national grid. So before the national grid was built, okay, you could build a power station. There it is. And there's the power station building. Okay. Power station. And you could feed your energy into local towns and cities. So that's our town or city. I'll put T in it. Okay. And you could charge what you liked. You could produce electricity at any voltage you liked. I think you could even do it at DC rather than AC. And then if you lived in a different city, okay, there'd be another company with their power station, charging their fees, generating at their voltage. And I think you're realizing here that this system, okay, has a problem, that devices on one city or town are not necessarily compatible with another one. I'll draw a third company that's decided to build a power station in a different city. Okay, so there's the little power station, cooling tower, power station, and I'll put that town here. So factories and buildings, etc. Okay, and you've got a real problem here, because apart from the fact it's a captive market, okay, if they're generating at different voltages all over the country, then what happens if you move house? Okay, you've got a problem, because you might have a power station here that's feeding you electricity at 120 volts, and then suddenly you go and live here, and none of your devices will work because they generate at 240 volts. Okay, and some of you will say, well, get yourself a transformer. Yeah, absolutely. Yeah, you'd need a step-up transformer in your house to do that, and it's a nightmare. Nothing was compatible. They generate electricity at 120 volts in America, and certainly when I was a kid and travelled abroad, you not only needed a adapter to change the pins on the plug, but you needed to make sure that your devices switched over to 120 volts to work in America, because they're generating at a different voltage. Okay, you literally can't take your hairdryer, your UK one, 240 volt hairdryer, and just with an adapter plug it in America. It just isn't going to work. Okay, so we're back in the UK now. Separate power stations, separate cities and towns. We'll connect them up. Okay, so there we go. You'll notice this is not in any way a grid system. It's an independent, separate system of connections. Okay, and what happens when this power station fails? That cable stops having electricity on it, and this town doesn't get any energy at all. That's not very good. Okay, there are amazing stories in London of two power stations feeding different sides of London, and you get a power cut and half the street would go out and the neighbours on the other side would have electricity. Okay, this is not a robust system. One or two of you will realise that what I'm going to do in a minute is very much like the internet works. Okay, so along comes the government and sets all sorts of rules and things and creates a national grid and says, hey, why don't you all, or you're going to all, generate at the same voltage? Okay, so you're going to make sure towns and cities get 240 volts. You're going to all generate with AC, because you have to use transformers, okay, and you're all going to generate at 50 hertz. The turbines are going to go round and produce AC of the same frequency, and then we are going to connect you all together. And the story goes that these connections were done without permission. Some engineers just one night gave it a go. So they knew all the power stations were working correctly at the right voltage, okay, and kind of secretly as an experiment, they joined them all together and it all worked. Now you might go, well, so what? But look what happens to this town here Yeah. When this power station fails, it can get energy from a different power station. Okay. You could even put cables in that sort of do this. Okay. So you'll notice that if this part of the grid fails or breaks, then there's another route for the electricity to travel along. So that's really clever. Okay. This became really important during the war. It was tested really well because in London they had power from Battersea Power Station, which I'm sure you've seen, and Fulham Power Station. And the power stations were damaged in the Blitz, but out they go. Okay. And it was actually South Wales power stations, they had a lot of coal in Wales, that via the national grid kept London up and running, and no doubt Churchill in his underground bunker doing all his plans that he did. You might have been in that museum. So look at the diagram and see just how clever the national grid is. It allows us all to use the same voltage, so we can take our devices into different towns and cities. It gives some control over the price and manufacture of electricity, and most importantly, it provides redundancy. So if one loop of the national grid fails, then there'll be another set of cables to keep the lights on. Obviously, if you're right on the end of a thinner wire that goes from a town substation to your farm out in the sticks, well, if that cable breaks, bad luck. They have to come and replace it. You haven't got a secondary redundant system there. But of course, that's not the high voltage power lines. These are the sort of super grid type high voltage power lines that go between power stations and cities. Just to end, you might have driven down the M6 Spaghetti Junction in Birmingham, and if you look over the side of the road as you go south, there's a massive substation there with all the national grid cables coming in and stacks of switches and transformers and circuit breakers that then feed the electrical energy into Birmingham. So I hope you now feel you've got a really good understanding of what the national grid is and how it works. So you do get a lot of questions on this at GCSE. Remember which bit is the national grid, and remember why it works so well. And also remember the maths of how boosting the voltage, stepping up the voltage, reduces the losses on the power cables. Anyway, I hope you enjoyed that video, and I look forward to seeing you before too long.